Hi everyone, and welcome to lab 4 of the course. In this lab we're going to design antennas on HFSS, more specifically dipole and horn antennas. So the first antenna we're going to design is a half wavelength dipole. So that's a wire antenna that has a length of lambda by 2 at the design frequency. Here I'm asking you to design the dipole at a frequency of 5.xx gigahertz, where as usual xx are the last two digits of your student number. In this demo I'm going to design it at 5 gigahertz, but when you guys follow along, make sure to use your correct frequency. So the first question is to calculate the theoretical length of the dipole. So of course you would calculate the wavelength at your frequency based on speed of light in vacuum, and then take half of that, and that would be the length of the dipole. So at 5 gigahertz, the length of the dipole will be 30 millimeters. Second question is to model the dipole on HFSS as a copper wire with a diameter of 1 millimeter and a length equal to the length of the dipole. So we can go ahead and start doing that on HFSS. So modeling it as a cylinder or a copper wire, so we need to create a cylinder. I want to create it in the y-axis, but you can create it in any axis you want. I'm gonna create it in the y-axis, so cylinder is gonna go this way. Okay, we can give that a good name here. So create a cylinder, we call that dipole. It's going to be a copper cylinder. You can change the material to copper. All right, so the center in the x direction will be 0, and y that will be minus the length of the dipole over 2. And z will be 0. So the length of the dipole, again, that would depend on your design frequency. But at 5 gigahertz, which is the frequency I'm designing at, it's going to be 30 millimeters. And then the radius will be the diameter of the wire over 2, which as per the specs is 1 millimeter. And then the height will be just the length of the cylinder, or the length of the dipole, so it would just be a L dipole. Perfect, so that's going to be the dipole. Next you have to place a port in order to excite the dipole, and normally the dipole is excited right in the middle. So on HFSS we actually have to create a gap and then place the port inside that gap. So to create a gap, I'm going to create another cylinder and then subtract it from the long cylinder. So I can simply copy this one and call it gap. And then the only difference will be the length. Here we can create a new variable called the length of the gap, and we can have that as 0.5 millimeter. So of course, theoretically, the excitation is at a single point, but because we're running a physical simulation, we have to have a certain gap to excite the dipole. The diameter will be the same, and the height will just be L gap. So you can see that's the gap that I want to take out from the dipole, and of course, to do that we can just subtract it. So subtract the gap from the dipole, and we don't want to clone it because we actually want to create a gap there. Perfect, so I just made a gap here for the port. Next I'm gonna design a sheet to be used as the port, so I can create a sheet, and that would be my port. And that needs to be right in the middle of these two cylinders here. So the position along x will be minus the diameter of the wire, over 2 because we want it to extend all the way to the ends of the cylinders. In y, that will be minus L gap over 2. And then in z, will just be 0. So in the x, that will just be d wire, and in the y, that will be L gap. I'm going to give that a different color here so you can see it. So right there, we've placed the sheet right in between the two cylinders, and that's where we're going to place the excitation or the port. All right, so now it's time to assign the port. If you guys remember, so far we've been using wave ports in all our designs, and we could do that because the excitation was at the edge of the solution space. But right now we have an excitation that's going to be inside our solution space, because next we're going to place a radiation box around the dipole. So here we cannot assign a lump port. We cannot assign a wave port. We have to use a lump port. So if you right click here, assign excitation, select lump port. So you can leave that as 1. In terms of the port impedance, so unlike a wave port where you can just not assign an impedance, a lump port has to be given a certain impedance. And here you need to have some prior knowledge about the impedance of the device you're designing. So for a dipole, we know that the input impedance is going to be 73 ohms. So we're going to assign the port impedance as 73 ohms. And another difference between a lump port and a wave port is that you have to assign an integration line. And that's simply a line that tells HFSS the direction of the current flow. So for us, it's going to go from one cylinder to the other. So we can simply go from here to here. And it doesn't matter if you want to assign it the other way. It's just the direction of flow in our case does not affect the results. It just has to go from one cylinder to the other. And finally, we're going to do the same thing as before, where we're not going to renormalize the port. Okay, so we've assigned the excitation. Next, we have to create a radiation box around the dipole. And the rule of thumb is the radiation box has to extend at least a quarter lambda on either side of your model. So for us here, it has to extend lambda by 4 in x in this direction and lambda by 4 in the other direction. So the total, let's say, width of the box has to be lambda by 2. In the z direction, the same idea, it's going to extend lambda by 4 in positive z and lambda by 4 in negative z. In the y direction, it's going to extend lambda by 4 from the end of the dipole. So that means the total length of the box will be length of the dipole plus lambda by 4 on either side, so lambda by 2 in total plus the length of the dipole. Okay, so let's go ahead and create the box, and you'll see what I'm talking about. Let's create a vacuum box. Make it transparent here so you can see inside. Give it a different color as well. All right, so the box, we can call that air box. So in the x direction, it's going to extend by minus, actually let's give it a width of air box over 2. In the y direction, it's going to extend by length of the dipole, or no, let's create length of air box over 2, and in z minus height of air box over 2. And then we'll assign those variables in terms of lambda. Okay, so the width of the box in the x direction, that would be a total of lambda by 2, so lambda by 4 on either side. So we can actually create a new variable called lambda, and in In my case, at 5 gigahertz, lambda is 60 millimeters. So 60 millimeters. And then the length of the box is going to be the length of the dipole plus lambda by 2. So the length is in the y direction. The height of the box will be simply lambda by 2. And then x size will be the width of the box, y size will be the length, and z will be the height. All right, so that's the air box, and it should be extending lambda by 4 at your design frequency in all directions. And typically, the larger you make the box, the better. But of course, the larger the box is, the longer the simulation will take. So lambda by 4 is sufficient. Okay, so the next step is to assign the boundaries. So we need to assign radiation boundary to all the faces of the box. So you can select the faces like that. So all the faces should be selected, and assign a radiation boundary. So I may not have selected the bottom face, so I'm just going to go ahead and delete that. I'm going to make the box slightly opaque so I can see. All right, so select this face, this face, this face. And then this face, and finally this face. Okay, so that should be good for the radiation boundary. Next step is to assign the solution frequency. So I would assign that as 6. It's larger than, actually let's say 7, because I want to plot the S parameters up until 7. So we'll set that to 7, maximum number 10 should be good, and maximum delta S is 0.01. Minimum number of passes, we'll set that to 6, and the minimum conversion to 3. And so I want to create an interpolating sweep to look at the S parameters, but I also want to look at the radiation or the fields at the design frequency. So I'm going to set an interpolating sweep from 3 to 7. And then I'm also going to go ahead and create a discrete sweep at a single point, which in my case is 5. Of course, you would do that at your frequency. And make sure that you save the field so that we can see the radiation pattern later on. Good, so with that, you should be good to go. One thing I will do now, which you can actually do after the simulation runs, is to create a far field setup, and that will allow you to plot the radiation pattern. I will explain the radiation pattern as this simulation is running, but you can create a far field setup now. So you want to create a sphere, and that's where the radiation pattern will be plotted. So the phi direction, as you guys know, it starts at x, phi equals 0, and it goes all the way around 360. And theta is the elevation angle. It starts at so at z it's 0, and then it goes clockwise, and it extends again from 0 to 360. So phi, I will go from 0 to 360, and let's say steps of 10, that should be sufficient. Theta, I'll go from minus 180 to 180. So that's good. And then we'll validate that, make sure everything is good. and then we'll run the simulation. So while the simulation is running, I want to talk to you guys about radiation patterns for antennas, which you may or may not be familiar with. But the idea of a radiation pattern is that it's the power, the distribution of the power radiated by the antenna in the space surrounding the antenna. So basically, you want to see, the pattern will tell you which directions radiate more power. If there is a null in the power, which means that there's a direction that doesn't radiate any power at all, and that's what the radiation pattern is it's basically telling you. It's the power distribution of the power that's radiated by the antenna. So when we talk about the 3D pattern, it's simply a shot of the power distribution in 3D surrounding the antenna. A 2D pattern is in a certain cut of that 3D radiation pattern. And we're going to be plotting all of those today for the dipole and for the horn. Okay, so the simulation was fairly fast. I'm going to check, make sure the convergence is good. So it looks like it's converged within 7 passes, and it met our convergence criteria, which is good. So the first thing we want to look at, so that's part C of the dipole question, is to plot S11 from 3 to 7. So we can go ahead and plot S11. So it's simply S11 in dB, and this sweep is the one that has the frequencies from 3 to 7. So you can go ahead and plot that. All right, so you can already see where this is going. The question is the dipole matched at the design frequency? So the best matching here is at this point, and we can put a marker there. So the best match frequency is 4.66 gigahertz, as you can see. So that means the dipole is not matched at the design frequency, because my design frequency was 5. So the next question is adjust the length of the dipole in order to get it to the design frequency. So how would I do that? So if my resonant frequency is 4.66 and I want to get to 5, would I make it shorter or longer? So think about that for a second. So of course, if I want to increase the frequency, I need to make the dipole shorter. So I need to reduce the L dipole in order to get it to 5. And since the simulation is fast, you can actually run a parametric sweep of the length of the dipole. So the dipole length now is 30, and I want to make it shorter than 30 in order to increase the frequency. I don't know if I said that correctly before. So if I want to increase the frequency, I need to make the length of the dipole shorter. So I'm going to go from, let's say, 26 to 30 in steps of 1. So whenever you run a parametric sweep, you always want to start with a few points, especially if the simulation takes a long time. So here I only selected from 26 to 30, and make sure you click update here, which means it will run only 5 simulations. And then I will narrow down where I want to run more points, instead of running steps of like 0.1 millimeter where I don't need to. Okay, so we're going to run those. And one thing that you can change in your settings in order to run the simulations in parallel is under HPC and analysis options. I don't know if I already mentioned that before or if you've already done it, but if you go here and unselect automatic settings and set a number of tasks and a number of cores. So it depends on which server you're running on, but usually the server would have 4 or 8 cores, and I usually say 5 tasks, 5 cores, which means it will run up to 5 simulations at the same time. So just if you don't want to wait for simulations to run in queue. Okay, so I have the parametric sweep here, so I'm gonna run that. And you can see here it's solving all the simulations in parallel. Okay, so the simulation's done. We can go ahead and look at all the results. So if you go under families, you can see that here it's plotting the nominal length for the variable, which means or the nominal value of the variable, which means it's the value that you set in the properties window. But if you go under edit, you can use all values. You can just say apply trace. And then you can see as you decrease the length, the frequency is increasing. And for me, it seems like it's between 28 and 27. So theoretically, I could run another simulation to get it exactly at 5. But I want you guys to just do increments of 0.5 millimeters. And whatever is closest, you can pick that. So for example, mine could be 27.5. And if it's like right in between, but I will just pick 27, and I will say that's just good enough for my frequency. So I don't want you to run a parametric sweep with 0.1 millimeter increments. Just a 0.5 millimeter is fine. So I think 28 millimeter is good, so I'm going to stick with that. So I will go ahead and change that in here, so 28. So that should change it in the model. Okay, so that would be the new length of the dipole in order to change the resonant frequency to the correct design frequency. The next question is, what's the minus 10 dB S11 bandwidth? So I'm just gonna go ahead and select just 28, so that we're looking at the one that I want. So of course the minus 10 dB bandwidth will be from here, and I can add another marker to here. So it seems to be about just less than 1 gigahertz of minus 10 dB bandwidth. Okay, so that's it for part C. I'm gonna go ahead and save that. The next part is about the radiation properties of the dipole. So of course, the dipole is an antenna, and as you guys know, antennas radiate electromagnetic waves in the space surrounding them. So based on this dipole, I'm going to go ahead and hide the air box. we can define something called the polarization of the wave that this dipole is radiating. And polarization by convention is the direction of the E field in the wave that's coming out of this dipole. So for a dipole antenna, the E field is going to be parallel to the dipole. So in this case, the polarization is in the y direction. So of course, if your dipole is in the x direction, the polarization will be along the x, will be along the dipole. But in this case, the polarization is along y. The next part is to plot the 3D radiation pattern, which is the total gain, or I'm asking you to plot the total gain at the design frequency, and what type of radiation does the dipole have. So in order to plot the radiation pattern, first you need to make sure that you actually have a far field setup. So make sure that you have that for theta and phi. And this one, if you forget to do it before you run the simulation, you can just simply add it after. It doesn't affect the results, and you don't need to run the simulation in order to get it. But what you do need for radiation is to run a discrete sweep, because a discrete sweep is going to give you the fields. That's what we need to plot the radiation pattern. Okay, so for radiation, you go under results, you right click, far field report, and we do want a 3 dB radiation pattern. So we'll go for a 3 dB, we want a 3D radiation pattern, and we'll do a 3D polar plot. All right, so you'll see here that for the solution, the only options you'll have are the solution frequency, which in our case is 7 gigahertz, and the discrete sweeps. So here we have the sweep 1, which is a discrete sweep. And if you go under families, you can see the frequency here is 5. The length of the dipole is going to be 28. That's the one that we settled on. It actually doesn't seem to have a solution at 28, so we may have to run that. So I'm just going to close that and make sure it's 28, and then I'm going to run the discrete sweep at 28. Alright, so we can go there and we'll get ready to plot it. So we want the total gain, and we want that in dB. We want this discrete sweep, and we want it at 26. No, we do want it at 28. Go for 28. Let's see if that runs. There you go. All right, so total gain, dB, we're plotting it for all phi angles and all theta angles, so basically in the 3D space surrounding the antenna. You can go ahead and close that. All right, so this is what the radiation pattern is. It's a distribution of the power surrounding the antenna. So it tells you where the power goes when it radiates out of the dipole antenna. So in this case, you can see here that there is high power, which is the red, in these certain directions. There is a null or a zero along the dipole, which makes sense. The dipole is a piece of metal, so it doesn't have any electromagnetic waves at it. So that's the general shape of the radiation or the power distribution surrounding the dipole antenna. All right, so what type of radiation pattern is this? I'll let you guys think about it, maybe search what types of radiation patterns there are, and then try to classify this radiation pattern based on that. All right, so the next part is to plot the copolarized and cross-polarized gains at the design frequency in two principal cuts. All right, so you guys can see that this power distribution that you see for the 3D case, it's descriptive, but it doesn't really tell us everything we need to know. So here I plotted the total gain. As you guys may have known, we do have two types of gain. We have a copolarized gain and a cross-polarized gain. So the copolarized gain is, of course, the gain which is along the polarization of the dipole. So this would be along the y. The cross-polarized is the one that technically should not radiate because it's perpendicular to the polarization of the dipole. And this type of radiation pattern does not tell us this information. So that's one thing we're missing in this case. Another thing is when you want to discuss radiation patterns, you normally want to take a certain cut. And from that cut, you would learn something about the radiation. And normally for antenna radiation, we select two cuts that are the most descriptive of the radiation. So if you look at this dipole, there are certain things that stand out. So the first thing you would want to know is that there is a null along the dipole. So this null would be something that our principal cut should capture. And the cut that would capture this null is one that is along here. So if you cut, like a top view here, if you cut into the screen and take a certain cut here, you'll be able to see this null. Another descriptive view is the one in this direction, which shows us that the radiation pattern does not change as you go around the dipole in this manner. So that's basically what I'm asking about. I'm asking you to plot the copolarized and cross-polarized gains at F0 in the two principal cuts. All right, so let's go ahead and plot that, and hopefully you'll see what I mean. So under results, you can go far field, and we'll plot that in on a rectangular plot. All right, so for the copolarized and cross-polarized, those will be gain phi and gain theta. Actually, before I want to go into the dipole so I can describe it better here. Okay, so if you go under the results, far field, rectangle plot. So co and cross polarized are gain phi and gain theta, and I'll explain why in a second. We want to plug those in dB. All right, so our primary sweep will be theta. So we want to go around the dipole this way or that way. So it will be as a function of theta, the radiation pattern that we're plotting. And the reason why I chose theta is that it's going to be the most descriptive cut along the dipole. So for each antenna, there's going to be the best way to describe the radiation pattern. And for a dipole in this orientation, doing a primary sweep in theta is going to be the best way to describe the radiation. And again, you will see in a second. You can also do it along phi, but theta is the most descriptive. And then here you can plot, so actually we want to plot it at 5, and we want to do this at 28 just to make sure we get the right things. You can also plot it at different phi cuts. So a phi cut is a plane cut where you want to see the pattern. So for this dipole, a phi 0 cut will be the XZ plane. Right? So if I select phi 0, that will be the XZ plane. So it will tell you what the radiation pattern looks like in the XZ plane. A phi 90 cut will be along the ZY plane. So it will tell you what the radiation pattern looks like along the ZY plane. And these will be the two principal cuts that will fairly accurately describe the radiation pattern of the dipole. All right, so let's start with phi 90. Because that one is the one that has the interesting case where the radiation goes to 0. So if I'm plotting on phi 90, so ZY plane, and I'm plotting gain phi and gain theta in dB, so one of them will be copolarized, one of them will be cross, and I'll explain which one is which in a second. But right now, if I plot this, you would expect that at theta equal 90, so z-axis is 0, here it's 90 and minus 90, you would expect that either gain phi or gain theta at theta equal 90 should go to 0, because from the 3D pattern, the gain went to 0 at those points. All right, so let's plot and see that's what we get. And there you go. So you can see here that at minus 90 and plus 90, our gain theta went to 0. So right away you can see that gain theta is the copolarized gain, and gain phi is the cross-polarized gain. And the cross-polarized gain is very low because the dipole is not radiating in the cross-polarization, of course. It's only radiating in the polarization along the dipole. And as I mentioned before, you can see those nulls. All right, so that's one descriptive view of that radiation pattern. The other one is along phi 0. So when phi is equal to 0, that's the other cut. And for that one, if you go back to the 3D plot, if you remember, there was no change along the copolarized gain. It was all red all around. So if I plot that again for gain phi and gain theta, one of them will be copolarized, one of them will be cross. I'll explain which is which in a second. If I create a new report, you'll see that gain phi is not changing as a function of theta, which means the pattern is constant in that principal cut, which again makes sense because if you look at the 3D plot, there was a cut where there was no change in the pattern. All right, so hopefully that makes sense. The idea of a 3D radiation pattern and then having two principal cuts of that pattern that describe it the best. Okay, so now back to the point of gain phi and gain theta, which is co and which is cross. So if you think about a spherical coordinate system, so let's go, actually let's I'm gonna close all of that. I'm gonna look at this one. All right, so let's look at the dipole here. All right, so think about spherical coordinate system of phi and theta. So gain phi is the gain along the phi direction, and gain theta is the one along the theta direction. So for this principal cut, so again, this depends on which principal cut you're taking. So this principal cut is phi 90, so we are in the ZY plane. So in this plane, which polarization or which coordinate theta or phi is copolarized and which is cross-polarized. So if you think about a spherical coordinate system, theta will be going this way. So theta will be along the direction of the dipole. So gain theta will be the copolarized gain. And that's why gain theta here is the higher value. So gain theta, which is going this way, maybe if I take another view here. Is it in, yeah, there you go. All right, maybe the other x. All right, so this is the ZY plane. So gain theta will be along the dipole, right? Because gain theta will be, or the direction theta will be this way based on the spherical coordinate system. Gain phi, on the other hand, it will be going towards x. So if I go back to the other view, gain phi will be along this way. So it will be perpendicular to the dipole, which would be the cross-polarized. And that's why gain phi here is the one with the lower value. If you take the other cut, it will be the opposite. So if you take the other cut, it will be the opposite because in this cut, we're looking at the ZX plane. And in this case, gain theta, which would be going from x to z or z to x, will be perpendicular to the dipole. So gain theta will actually be the cross-polarized, and that's why gain theta here is low, Gain phi, on the other hand, is going from x to y, so it will be along the direction of the dipole. And that's why gain phi is the copolarized gain. All right, so hopefully this gain phi, gain theta, copolarized, cross-polarized makes sense. We'll go over it again in the horn antenna design if you don't get it from this explanation. All right, so next question is, what's the broadside gain of the dipole? So when we talk about broadside gain, it's usually the highest gain of the dipole. So in this case, you can either take it from this plot or from the other plot. The broadside gain will just be the gain at this point. So you can add a marker here, and it's 2.54 dB. Some of you might be wondering why this gain is higher than the maximum theoretical gain for a dipole, and that will be one of the questions that you'll have to think about in the report. So the broadside gain, or the highest gain or directivity of a dipole, is a certain number, which you will find out, and then you'll compare it to that and try to think about why there is a difference. Okay, so with this, that should be the end of the dipole section. So I'm going to move on to section 3, which is the pyramidal horn antenna. I'll go ahead and save that. All right, so a horn antenna is simply a waveguide that's flared in order to match the waveguide to free space, and in the process radiate the energy to free space. So the idea of a horn is actually fairly straightforward, and it's one of the oldest antennas that were designed. So the idea is, again, you have a waveguide, and you flare one end of the waveguide in order to match that end to free space. And as you guys know, if you have perfect matching to something, you basically transfer all the power. So in that case, the horn will radiate all the power from the waveguide to free space. So let's go ahead and create another HFSS design. So in the lab manual, I'm giving you the dimensions of the waveguide, length, width, and height, and also I'm giving you the flare of the horn in the H plane and in the E plane, as well as the length of the horn, of course. Okay, so let's go ahead and start with the waveguide. So normally antennas are designed so that their maximum gain is in the Z direction, but this is just a convention. You don't have to do it this way, but that's why when I design the waveguide now, I'm going to design it so that it's pointing up towards the Z, and the horn will flare towards the Z. But you could also do it in the Y axis. It's really up to you. The results should be the same. Okay, so waveguide design. So we're going to go in draw here and build the waveguide. So this would be the waveguide, and we can leave it as a vacuum waveguide. The X direction, let's make that the width of the waveguide. A little frozen here. Lost the VPN connection. There we go, we're back. Okay, so we'll have it so the width of the waveguide is an X, so we can create a variable called waveguide width, and then we'll do it so the height of the waveguide is in Y. So we'll do height of the waveguide here, and we'll start at z equals 0. All right, so the width of the waveguide is 23 millimeters. The height is 10. Good, and then the length of the waveguide is 100 millimeters. All right, so there you go. That's the waveguide. The next step is to flare the waveguide to create the horn. So there's a lot of ways to do that. I'm just going to take the way that I'm used to, and I think it's probably the easiest way to do it. So I'm going to create a surface on top of the waveguide here, which is the same dimensions as the waveguide, and then I'm going to create another surface a certain distance away. So I'm just going to create another surface on the top here, which is at the location where the horn is going to end, and that surface would have the same final dimensions as the horn. And then I'm going to connect the two surfaces to create the object, which is going to be the horn. So if you follow along, you'll see what I mean in a second. Okay, so I'm going to create a surface here on top of the waveguide. So this will be we can just leave it as rectangle. So this will have the same dimensions as the waveguide, and it's going to be on the top of the waveguide. So I'm just going to fill this out. Actually, this will be L waveguide. And the X direction is going to be like that, and here, and I'm going to give it a different color so we can differentiate it from the waveguide. All right, so that's the first surface. The second surface will be the final dimensions of the horn in terms of how far away it is from the waveguide, and the E flare and the H flare. All right, so E flare and H flare. So based on this waveguide, and assuming that we're exciting it with the fundamental mode, what is going to be the direction of the E field? So as you guys know, it's going to be in this direction. So in the Y axis, that would be the E field, and the H field is of course going to be perpendicular to that. So the H direction is along X, the E direction is along Y. So just keep that in mind. So the second rectangle will have a width in the X direction, which is the H flare. So in the X direction, it's going to extend by H flare, or the final dimension will be H flare. So here I'm just going to say H flare, and that one is 46 millimeters. In the Y direction, it's going to extend by E flare, and that one is 36 millimeters. And in the Z direction, it's going to extend by L horn, so the length of the horn. So that's going to be the length of the waveguide plus length of the horn. And of course, from the lab manual, that's 76 millimeters. All right, so over there, and we just need to fill this out with H flare and E flare. So that's going to be where the horn ends. All right, so if you just rotate that, this is going to be where the horn ends in free space. All right, so the next step is to select these two these two surfaces, and simply go under Edit, Surface, and Connect. And that will create an object connecting these two surfaces. And basically that's the horn design. Next we have to set the excitation, and of course that's going to be at the bottom of the waveguide. So this face here, this will be the excitation, and as you guys have been doing, it's just going to be a wave port. Next we have to set a radiation boundary. So here you have two options. You can either create a radiation box that's lambda by 4 away from the horn, but for the horn antenna, simply having this face as a radiation boundary actually does the job, and you get very accurate results. And of course, the simulation is a lot simpler. So for the radiation boundary, we will simply assign the top face as a radiation boundary. Good. These are all vacuum or air, that's fine. And of course, if you don't assign any other boundaries, HFSS will assume that all these outer boundaries are PECs, which is what we want. All right, so I'm just going to give that a name as well. And of course, this horn is called a pyramid horn or a pyramidal horn, because it's well, it looks like a pyramid, and because it's extending both in the H direction and the H direction and the E direction. Okay, so next step is to set the solution frequency. So we'll set that at 20 because that's the maximum frequency we're interested in. All other settings you guys are familiar with. Good. So we're interested in the S parameters from 8 to 12. So we're going to set an interpolating sweep from 8 to 12. And we're also interested in the gain from 8 to 12 in steps of 1 gigahertz. So we'll have to add a discrete sweep for that. So if you go under setup, add, and we'll do a discrete sweep. And we can do a linear step from 8 to 12 in steps of 1 gig. And we'll save all the fields. So that's just 5 points, which is not bad. All right, the final thing we need to do is to set the far field setup, which is going to be the same thing as before. So phi is from 0 to 360. And the reason why I set the step size in phi at 10 and in theta at 2 is because a lot of times the theta is the most descriptive variation. You will see that I did that in the dipole, if you remember, because the variation along theta is what I used for the 2D plots. And same thing here for the horn. When I orient the horn along the Z direction, theta becomes the most descriptive. Again, you might have to get used to the spherical coordinate system if you haven't used it in a while. But basically, theta going from minus 180 to 180 describes the full space. And I use a step size of maybe 2 or 1 because that's the most descriptive, and that's where the 2D plots will be plotted. Okay, with that, you should be good to go. Validate, everything's good. Now we can start looking at the questions here. So what is the polarization of the horn? So again, the polarization is always the direction of the E field. So this horn antenna is going to radiate electromagnetic waves, and the E field is going to have a certain direction. Of course, that's going to be based off the direction that it's coming out of the horn. And in this case, because the direction of the E field in the waveguide is Y, the polarization of the horn will be along the Y direction. So that's part A. Part B is asking to plot the 3D radiation pattern of the horn at 10 gigahertz. So once the simulation is done, we'll go ahead and do that. We can start far field 3D polar. So total gain dB, and we will select sweep 1 so that we can select 10 gigahertz. And we'll just wait for the simulation. All right, simulation is done. So we can just go ahead and create the report. And there it is. So that's the 3D radiation pattern of the horn at 10 gigahertz. Now, the horn antenna is special because when we talk about the principal cuts, it's actually simply cuts in the E plane and the H plane. So if you look at this pattern here, the most descriptive views will be one looking at it from this direction, so that would be this cut, and the other is looking at it from this direction, which is this cut. And you can already see that one of them is at phi equal 0, and one is at phi equal 90. And if you look at the horn, phi equal 90 is the H plane, so that would be one principal cut, and phi equals 0 is the H plane, and phi equal 90 is the E plane. So the E plane is the plane that's along the same direction as the E field. The H plane is the plane along the same direction as the H field. And also one interesting thing that you can do is you can show this on you can show the pattern in the window. So if you show the 3D, so here you can kind of see the pattern on the horn. Maybe there's a way to make this bigger. Yeah, if you guys figure it out, you can let me know if you can make this radiation pattern a bit bigger, so you can see how it's coming out of the horn. But that's the basic idea. So we want the next question is asking about copolarized and cross-polarized gains in two cuts. So this cut will be the H plane cut because it's phi equals 0. This will be the E plane cut, phi equal 90. All right, so let's do that. I'm just gonna remove that from here. So we go under far fields, and copolarized and cross-polarized, again, gain phi and gain theta are the two that you're looking at. We want to plug those in dB. And for the E plane and H plane, we want to plot them at 10 gig. So select 10 here. All right, so again, at phi equals 0, that would be the H plane. So actually, let me do that here so you can see it. All right, so before I plot this, I want you to think about it for a second. So which gain phi or gain theta will be the copolarized? So polarization is along the Y, right? That's the direction of the E field. Now if I plot in the phi equals 0 plane, so that's the ZX plane, gain phi and gain theta, one of them will be copolarized. So which one would it be? So would it be gain theta, or would it be gain phi? So if you said gain phi, you would be correct, because gain phi is going to be along the E plane. Gain theta is going to be, the gain phi will be along the E direction, gain theta will be along the H direction, so it would be cross-polarized. So let's plot that. And there you go. So gain phi is the copolarized gain. It's the one that has the higher gain. And gain theta is the cross-polarized and has low gain. Perfect. So that would be the H plane, because it's at phi equals 0. The E plane is going to be at phi equal 90. So you just change it to 90. And you can see that we now switched. Gain theta became the copolarized, gain phi became the cross-polarized. So hopefully this makes sense. Gain phi, gain theta, co and cross-polarization. If you still have questions about that, you can always ask me. Okay, so I'm just going to label those here so that you guys don't get confused. So this one is the E plane. So E plane is along 90, and H plane is the one along 0. All right, so Question E is asking what's the broadside gain of the horn, and again that's the highest gain here. So you can either do it from this plot or the other one. In both cases, it should be the same. So here it's 10.7, and over here it should be the same gain. So at broadside, and it's exactly at 0. So 12.7, not 10.7. So these two numbers should be about the same. Yeah, they're exactly the same. Good. Next part is asking, based on the copolarized gain in C, so that's in the E plane, which is the one we're looking at now, calculate the half power beam width and the front to back ratio. So the half power beam width is the range of angles where half of the power has radiated. That's why half power beam width. And that's simply 3 dB on either side of the maximum gain, right? So the maximum gain here is 12.7. So if you put a marker, that's actually, let's do a delta marker. So if you select that, you can add a delta marker. All right, so this marker, we want it to be 3 dB down from marker 1. So if you move it so that it's about 3, so it seems like it's between these two angles. So what you can do is you can actually increase the resolution without having to rerun the simulation. So here, if you go under infinite sphere, you can increase the resolution. If you just do a step of 1, it might take some time to calculate, and here you can see that's about 3 dB, right? So from 12 to 9. So minus 21 degrees on this side, and if you do the other side, it's going to be the same because it's a symmetrical pattern. So the half power beam width will be from minus 21 to 21, which makes it 42 degrees. So that would be the half power beam width. Front to back ratio. So the front to back ratio is the ratio between the power in the broadside direction, which is the maximum direction of radiation, and the backward direction, which is 180 degrees away. And that will simply be the difference between marker 1 and whatever this power here at the back. So if I add a marker here at minus 180, so we are measuring minus 24.9 dB. So 12.7 minus 24.9, that will give you the front to back ratio. And of course, for a directive antenna, we want the front to back ratio to be as large as possible, which means the antenna is favoring the front more than the back radiation. So here will be the front to back ratio will be 37 point something. You can do this calculation. So it's 12.7 minus 24.9. Good. All right. So part F is done. Next is plot S11 from 8 to 12. So we've already had an interpolating sweep for that, so you can add S11. It's the correct sweep. Good. All right, so S11 from 8 to 12. And does the antenna have a good matching across the band? So the reflection is minus 22.5, which is very, very low. So that means the antenna does have a good matching across the band. That's good. Part H is asking about the broadside gain from 8 to 12. So basically it's asking about the gain from 8 to 12 at the broadside direction. So what you can do here is plot from the far field. So you can go under far field, rectangular plot. You can make the primary sweep the frequency, and of course select the right sweep. And you want to plot you can plot the total gain. And it doesn't matter which direction you plot it at in terms of phi, because it's going to be the same for all theta. So for theta equals 0, that's the broadside direction. And let's plot at phi 0. So that will give you a variation in frequency of the broadside gain. So let's go ahead and plot that. All right, so you can see here the gain from 8 to 12 as a function of frequency, of course, and at 10 here, what do you expect it to be? If you set 12.7, you would be correct because that's what we measured before. So if I plot it at 10, and there you go, it's the same number that we found before. So the gain of broadside at 10 gigahertz is 12.7, and you can see the gain variation as a function of frequency. Now, next part is asking based on the results from G and H, so based on the results from the S parameters and this plot, does the horn antenna exhibit wideband performance? So I'll let you think about that. I'll let you think about the answer to that question. Okay, so that's the end of the 3.1 pyramidal horn section. The next two parts are for you guys to complete. So the next part is an E-plane horn antenna, and that's an antenna that has a flare in the E-plane only, which means that the H flare will just be the width of the waveguide. So for that one, you would simply I can just show you how to do it. I can just copy that here. So that would be E-plane horn. So that means if it's only flared in the E plane, the H flare will be the same as the width of the waveguide. So if we do that, and you can see here that the flare is only in the E direction, right? Because it's only flared in the Y direction. So that's section 3.2. So there's some questions about that you guys are going to answer. Section 3.3 is to design a coax to waveguide transition. So that could be somewhat challenging, and I want you guys to think about it. I can show you what the final design looks like, so you have an idea. So in this section, you're going to design a coax to waveguide transition, and then you're going to add a horn antenna after that. So it's going to be coax, waveguide, horn. That's the flow. So I think it's this one. Yeah. So that's going to be the coax to waveguide transition. So I'll let you work on that on your own. All right. So that's the end of the demo. I will see you guys during the lab. The lab manual will be uploaded as usual, and please follow the report guidelines. All right, I'll see you guys then.